Here we have an exponential decay function, and the problem for us is to figure out, this is a radioactivity decay function, and the problem for us is to figure out what the half-life is, and what does it mean to ask what is the half-life. Um, well, looking at our exponential function and putting together a graph of it over here, a of t is our dependent variable. So this is the radioactivity rate. It would be, in units, something like counts per second, perhaps. And t is our independent variable. It would just be the time. It could be in years or seconds or some unit of time. And when we're asking what the half-life is, we're asking basically how long it takes for the radioactivity to decrease to 1/2 of its initial value. So we come down here on the graph, and then we're looking out across the plot to that function, and we're dropping a line from that point and onto the time axis, and that time then corresponds to the time that it would take for the radioactivity to drop to 1/2 of its initial value. So we know something about this relationship. We have some information, so we can rewrite that equation. Our a of t now is now just equal to a0 over 2. We're looking at a specific value of a, and we can say then that a0 over 2 is just going to be equal to a0 times e to the minus lambda. This would be a decay constant that you would be given in a situation like this, usually if you're trying to figure out what the half-life is, and we're just using the subscript t1/2 in order to identify this as a specific time. Now in this equation, the a0's are going to cancel out. We can divide both sides of the equation by a0, and that will leave us with 1/2 is equal to, and we have e to the minus lambda t1/2. Now we know that these exponential functions, we're trying to solve for a variable which is up here in the exponent, and we know that the way we can get these exponents down so that we can work on them is to take the logarithm. So in this case, we take the natural log because we are using the base e here. And so we'd write this down as the natural log of 1/2. And this would be equal to the natural log of e to the minus lambda t1/2. Okay. Now we know that when we take the natural logarithm of anything, log of a to the b, for example, we bring this exponent down in front. So we have b times the natural log of a. Over here in this expression, we're going to bring the exponent down in front. So this gives us the natural log of 1/2 is equal to minus lambda t1/2 times the natural log of e. We should know that the natural log of e, it's the power that you raise the base e to in order to get e. So we know that this is going to be equal to 1. And this just gives us then that we have the natural log of 1/2 is equal to minus lambda t1/2 And from there, it's a simple matter to solve for t1 half. T1 half is just going to be equal to, we'll take the natural log, calculate whatever the natural log of 1/2 is, and we'll divide that by the decay constant minus the decay constant. And that's our answer. The decay constant will have units of inverse years because we know that the exponent here has to be dimensionless. So t will have units of years, let's say, and lambda would have units of inverse years. So we might have something like lambda equal to 1 times 10 to the minus 7th years. So that's your half-life problem. That's all there is to calculating the half-life.